All right, so last week we covered Raoult's law. This, just a summary, is an equation that you can use to find the vapor pressure, aka just the pressure of a solution, based on the mole fraction of the solvent added to the total solution and the original vapor pressure of the solvent before the solute is added. Now, also, if anyone has any questions about last week's lesson or about this law, we can begin. All right, let's begin then. All right, phase diagrams. Now, the one on the left is phase diagram of water, and the phase diagram on the right is of most substances. Let's just focus on the one on the right for now. So, on the figure on the right, you can see that the x-axis is temperature, the y-axis is pressure. And so if we look at a constant pressure, let's focus on, let's say, this point right here. Let's assume that this is like, I don't know, 1.2 atm, something like that. As we go up from temperature, a certain substance will go from a solid to a liquid to a gas, and it'll go from solid to liquid, that's melting, liquid to gas, vaporization. I'm sure you know about all this already. And the reverse is condensation and freezing. And also, in case you forgot, sublimation and deposition. This is just when the phase change between solid and liquid to a gas is so fast that it's as if it was just a phase change from solid to gas and vice versa. Now, let's look at it a little bit differently. Let's say we were at a constant temperature and we were to increase the pressure. Let's say right over here. Let's say this temperature was, I don't know, 30 degrees Celsius. It would first go from a gas, but then as you increase that pressure, that distance between the molecules is going to become smaller and smaller until eventually it'll go from a gas to a liquid as the pressure exerted increases, and then eventually from a liquid to a solid, because the distance between the molecules for a liquid is much bigger than the distance of the molecules between the solid. So as pressure acts on these molecules, that distance becomes smaller and smaller until eventually becomes a solid. Now, does anybody have any questions about this? Please unmute. I can't see the Discord text chain right now. All right, no questions. Now let's move on to the phase diagram for water. Now, as I'm sure you've noticed, the line that represents melting and freezing is going the opposite direction. It has a negative slope as opposed to the positive slope that you can see for most chemical substances. Now, let's focus at a certain temperature just to understand this diagram better. Let's say right over here, this is 0 degrees Celsius. Now at 0 degrees Celsius, if we were to increase the pressure, water vapor, which is the gas form of water, this will go from a vapor form directly into a solid. So that is the deposition process. That's not going from gas into liquid and then into solid. It's going from gas straight into solid. Why, you may ask? Well, this is because water is actually at its most dense when it's a liquid. Now, because of this, when pressure is applied going from that about 0.006 mark that's labeled on the y-axis, at this point, the water vapor condenses to become ice. And then from there, once you apply pressure more and more and more, once you reach past 1.0 atm at this temperature, that ice will then become water because the distance of water molecules is actually closer together in liquid than it is in solid. That's why ice will float in any drinks that you put in it, because the ice is less dense. The molecules are spread further apart than in liquid form. Now, does anybody have any questions about this? All right, let's continue. Combined gas law. Now, this is a equation that can be used. You can figure out the pressure, volume, or temperature of a system after a certain stress has been applied, as long as if you know all the variables except for the one that you're trying to find. So let's look at this example right here. If you had 20 milliliters of a gas at 25 degrees Celsius and it was at a pressure of 1.2 atm, but then the conditions of the gas were to change to become STP. In case you forgot this from last week's lesson, STP is standard temperature and pressure. That is 1 atm, and 0 degrees Celsius or 273 Kelvin, this problem is asking you for the new volume. Now, this is the actual way that you're supposed to find the answer. Let's see, you have the first pressure that is given, which is 1.2 atm. You have a volume of 20 milliliters. This converts to 0.02 liters. And your total temperature is 298 Kelvin, because 273 plus 25 degrees Celsius, that becomes the value in Kelvin. And then this is all the conditions of this gas before the stress is applied. Now, after the conditions change, the pressure is now 1 atm, and the second temperature is 273 Kelvin. From there, you can solve for V, and then using just basic algebra, and then you should get an answer of 22 milliliters. I know you guys typed in answers with 3 significant figures and was it 4 significant figures? That's okay, yeah, but I mean, even though the volume of the gas is given in 3 sig figs, the rest of the values given are only in 2. So if you're following standard sig figs rules, it would be only 2. But sig figs, it's okay. I know some people only go by just whatever unit of volume, whatever unit that the question is asking for correlates to whatever number of significant figures the question mentions for that specific circumstance. So because there are 3 sig figs for volume, you might have done that, and that's okay. I won't really be taking off points for sig figs because that's just a whole deal. All right, let's move on. Now, ideal gas law. This is something that you should not have seen before unless if you were studying for Science Olympiad outside or studying for AP Chemistry. Now, the standard gas law, it's similar to the combined gas law, but now you are taking the number of moles, we are introducing a new constant, and that's pretty much it. And now this is just another way of finding out just one of the variables, pressure, volume, temperature, or the number of moles of a certain substance after, if you don't know that certain variable. Now, PV equals nRT, or Puvner, as you may hear some people say, or myself say. The N in this equation represents the number of moles, and P is for pressure, V is for volume, T is for temperature. But now R is a new constant. This is one of many gas constants that you will see, but this is the main one that you probably will see. And R in this case is equal to 0.08206 liters times atmosphere divided by moles times K, or L times ATM times mole to the power of -1 times K to the power of -1. That might be another interpretation that you may see. Now, in your calculations, maybe you're only using 3 sig figs, you may be using 0.0821. It just really depends on the circumstance and your personal preference. Now, I would like everyone to try the problem on the right. When 0.45 moles of hydrogen gas are at 1.2 atm, or atmosphere, and 25 degrees Celsius, what is the volume of this hydrogen gas? And the answer is 9.17 liters. I know in this case I used the wrong sig figs. 9.2 would technically be the right answer, but as I said, sig figs, they don't matter too much in these problems where the numbers are still pretty small. Now, Puvner, you can from there use basic algebra to isolate the volume variable, and then from there you can plug everything in. You know there's 0.45 moles, you know the gas constant, which is 0.08206 units, and then you also know the temperature, that is 298 Kelvin, so 273 plus 25 degrees Celsius is the conversion to 298 Kelvin. And now you divide all that by the pressure, which is 1.2 atmospheres. From there, you get 9.17 liters, or 9.2 liters to be more accurate. Now, Graham's law of diffusion. What this law essentially states is that as the mass of a certain volume, of a certain gas increases, that the velocity of that gas will also decrease proportionally to the square root of its mass. Now, the picture on the right, that shows the exact numerical relationship, but just to keep in your mind, the general relationship is that the lighter the gas is, the faster it will travel, the greater velocity, and the heavier it is, the slower it will travel. Now, I hope you guys do have periodic tables handy. If not, just Google one. should be just on the internet. Will H2 or CO2, hydrogen gas, or carbon dioxide diffuse faster, and by a factor of how much? And yeah, so this is just uh, the gram formula mass. And now from there, you can just plug this into Graham's law of diffusion. Uh, and then from there, you get by a factor of square root of 22, which is 4.7. So good job. I just left it in square root of 22 in this case. But yeah, you are still correct. All right. In fact, I actually think your answer is considered more correct than mine. Yeah. All right. Let's continue. All right, Dalton's law of partial pressure. Now, this law essentially explains that when you have two separate gases or however many gases in a certain container, the pressure of all the gases inside a container are equal to the sum of the partial pressure of each gas in said container. Seems pretty intuitive, right? Let's try a practice problem on this. Before we begin that, actually, there's one thing that I forgot to mention. This has to be within the same container. As soon as you start switching the volumes of the container, these also will change proportionally. So you also have to keep that in mind. I would look to the combined gas law as to the exact relationship as to these units of pressure, temperature, and volume. Now let's look at this practice problem right here. If you have 0.5 liters of oxygen at 500 kilopascals, and this were mixed with 0.2 liters of nitrogen gas at 55 kilopascals, and this is all combined into a 1 liter container, what is the total pressure in this new container? All right, so let's break this problem down into its subproblems, if you will. Now, we know the pressure of oxygen is 50 kilopascals in a 0.5 liter container, but we're trying to find its partial pressure in a 1 liter container first, so that then we can use Dalton's law of partial pressure, add those two partial pressures together, and then we can find the new total pressure in this container. Now, as you can see here, the pressure of O2, in order to figure it out, we can just use proportions. Now, the pressure of O2 we know is 50 kilopascals. You can set up a proportion and you can multiply this by the value in liters, and then you can set that equal to the new volume of the new container, which is 1 liter multiplied by the new partial pressure of oxygen in this new container, and that turns out to be 25 kilopascals. This is the same if you did division or whatever. This is just a proportion. Now, if we look over here, for the pressure of nitrogen in this new container, you multiply the volume by the partial pressure, which is 55 kilopascals and 0.2 liters, and you set that equal to the new volume of the container, which is 1 liter, multiplied by the new partial pressure of nitrogen in this new container. Again, this is a proportion, basic algebra. You could use divide or anything, just, you know, throwing that out there. And then from there, the pressure of nitrogen in this new container is 11 kilopascals. Now, since Dalton's law of partial pressure, that's a tongue twister, is stating that the total pressure of the new container is the sum of the partial pressures of each gas, and you now know the partial pressures of each gas, you just add those up together. And then from there, 25 kilopascals plus 11 kilopascals is 36 kilopascals. That is the total pressure of the system. Nathan, I think you said 36 kilopascals. Good job. All right. The van der Waals equation. This is something that you won't see often, but I feel like it's still good for you to know. This is based on the ideal gas law right here, PV equals nRT, Puvner. Now, Puvner, this is essentially a relationship that is used just for ideal gases. But as you said before, in the kinetic molecular theory of gases, ideal gases differ from the everyday life gases that we see, and the ones that also apply in our experiments too. Now, P equals nRT, you should recognize that, that's the basic structure, but then you have nRT divided by V minus NB, And this new fraction is now also being subtracted by n squared a over v squared. Now n, r, t, v, and p, these are all just the standard variables that we've covered already. But now b and a, these represent constants, and essentially the relationship, b is supposed to represent, as it says on the screen, the correction for the volume of the molecules. And so as the volume of a certain gas will decrease, the number of molecules will also be correlated to that. So the purpose of the B constant in this case is just to, as it says on the screen, just to correct for this volume, because as we said before, ideal gases, they do not have a volume, but real gases, they actually do have a volume that is not negligible. Now, the variable for A, this also accounts for, but now A accounts for the attraction between molecules. We said with KMT that ideal gases, they don't have an attraction to one another. These molecules in these gases, they're not supposed to have attraction to each other, and that's what makes them ideal gases. But with real gases, there actually is an attraction, and you do need to account for that. So that's why that main fraction on the left is being subtracted by this new proportion involving this new constant that accounts for that. Now, this attraction between the gas molecules, that's going to lower the pressure of a certain gas, because these molecules, instead of applying pressure to the sizing container or just around its environment, is going to be limited because it's attracted to other molecules of itself. That means the pressure is going to decrease, so you can see why the second fraction, this proportion, is being subtracted. Now, let's look at the value for B. B is supposed to be a correction for the volume that a gas will actually occupy. So with an ideal gas, you just had a certain volume container and that is it. But because these gases also have a volume of their own, you need to subtract that ideal volume by this certain volume of the gases. And that is how you will actually generate an actual accurate number, because the Pufner equation only accounts for ideal gases, and it doesn't account for the fact that gases do actually have a volume of their own. So you need to take this out of the Pufner equation in order for you to get an actual value for pressure or temperature or the number of moles. Yeah, so this equation, I know it's pretty complicated. I went through it pretty fast, but I only went through it fast because you will not see it in really anything. You just need to know the general relationships that I just covered right now. All right, solution stoichiometry. We're going to move on from gas stoichiometry, gas behavior, stuff like that. Now, I know I covered in an earlier lesson just the basic units of chemistry. I covered molarity, I covered molality, I covered percent and percent of volume and mass, and I also covered ppm, which is parts per million. Now, if you forgot about this, just go back to it after this video lesson. But now I'm just going to move on to basic stoichiometry, unless if anyone else has any questions about gas stoichiometry, about what I've covered today, or about, I don't know, just something. All right, I'm going to take silence as no questions. All right. Law of conservation of mass, matter, and energy. I'm sure if you've taken any science class at our school, you should have heard this before. It's covered in physics, chemistry, and living environment, I'm pretty sure, and earth science, I think. All right, so, mass, matter, energy is created nor destroyed. It's only converted from one form to another. Yeah, but the more important part of this slide is percent error and percent yield. These are used in experiments. These are really values that you will see a lot in experiments, values that you will have to calculate. So for percent error, you've got, it's just the measured value that you got for a certain unit. You subtract this by the true value, take the absolute value of this so you can see just the general percent change. And then you divide this by the actual, what is considered true and accepted by standard scientific units, and you multiply this by 100 in order to switch it to convert it from a proportion into a percentage. Now, percent yield, this one might be a new one for some of you. Percent yield is the actual yield that you get from a chemical reaction usually, and you divide this by the theoretical yield. This is the one that is done by calculations. More on that later, but yeah, you essentially divide these values and you multiply it by 100 to get a percentage. On the theoretical yield, we will cover how you actually get that in the next few slides. And the actual yield is the value that you get for within an experiment context, where you actually physically do conduct the experiment rather than just simply calculating it, because real life conditions differ from theoretical calculated conditions. All right, now a balanced equation. This is very important for the theoretical side of chemistry. I'm sure if you take a chemistry class, you've seen this before. If you look at the example at the bottom, C2H6 plus O2 yields H2O and CO2. Yeah. What is it? The coefficients that are in front of species, and the equation on the bottom, you won't see the numbers. That is because this is a problem for later on, but usually in a balanced chemical equation, you're going to see coefficients in front of it, just like how you'll see it in math. Yeah, so let's say there's like a 2 in front of the O2, the oxygen. This would mean that for every 1 mole of this reaction, there's going to be 2 moles of oxygen produced to produce whatever new proportion with the new coefficients of water and carbon dioxide. Now, let's see. Now, you can use this same principle that I've described to then develop a mole ratio. And this will determine, let's say, for every 2 moles of oxygen in this reaction consumed, it produces, let's say, 6 moles of water. That is a mole ratio, and you're going to need to know your proportions really well to gain mastery over this skill in chemistry. And now, as I mentioned before, because of the law of conservation, the number of atoms between the product side and the reactant side, these must be the same for every single element, every single chemical species. And this is to preserve the law of conservation. Otherwise, you start breaking a basic law of nature. And now you see this example on the bottom. Based on bullet point C in that case, I would like you guys to just quickly balance it. Remember that for each element, it has to be the same number of atoms in the reactant as there is for the product. So yeah, please keep that in mind. Those subscripts at the bottom, in case you don't know, those represent the number of atoms of that certain element within that chemical species. So I'll give you a minute for you to balance that. And in case you forgot how to balance it, I will be covering how to do a certain strategy later. All right, so if we look at that first equation with all the colors, this first equation is just the first iteration of trying to balance it. So if we look at the first reactant, C2H6, we want 2 carbon atoms to be in the reactant, since they already are, and 2 carbon atoms in the product. So if we look at the green color right here, so there's 2 over here, we want 2 atoms of carbon in the product, so that means CO2, we're going to want to change that to 2 moles. So now the mole fraction between C2H6 and carbon dioxide is 1 to 2. And then from there, hydrogen. If we want 6 hydrogen atoms on the reactant side, we want 6 hydrogen atoms on the product side. So since there's already 2 hydrogen atoms in every 1 molecule of water, we need 3 moles of water in order to correctly balance this equation. And then from there, we run into a problem with oxygen. Now, because of all those changes that we made for this species, it means that now there are two oxygen atoms here, and then 3 oxygen atoms here. So that makes 5 oxygen atoms. Now, with 5 oxygen atoms and only O2 species being a reactant for oxygen, that means that you're going to have 2.5 moles of oxygen. Now, in a chemical reaction, in a chemical equation, you would want to use whole number coefficients. And so because of this, we are going to change this again. Now, since we know that this oxygen molecule has 2 oxygen atoms, that means then we're going to want an even number of oxygen molecules in the product. How we can do that exactly? Well, if there's 5 oxygen molecules to the right, to the product side, then if we multiply that by 2, an odd number multiplied by 2 will always become an even number, 10. So now we change the coefficients, we double it, so 2 becomes 4, 3 becomes 6. And now those changes need to be reflected elsewhere in this species, C2H6. Now there are 4 carbon atoms, which means that since C2H6 has 2 carbon atoms, you have 2 moles of this species, and that means there are 12 hydrogen atoms on the reactant side, and there's also 12 hydrogen atoms on the right, because 6 times 2 is 12, and 2 times 6 is also 12. Now we need to correct for the number of oxygen molecules. So 4 times 2, that's 8, and 6 times 1, that's 6. 8 plus 6 is 14, 14 over 2 is 7, so now we have 7 moles of oxygen. Does anyone have any questions about this? All right, if no one does, we are going to move on. Now, limiting reactant stoichiometry. This is this was to describe what happens when you have only 2 limited sources of reactant. So you don't have an infinite amount of one reactant, and then from there you can figure out your proportions. You're limited on both reactants in a chemical reaction. Now, the way you do these problems is you're going to want to find the chemical equation balanced first, and then from there, you can use proportions to identify the limiting reactant, and then with the proportions side of this, you can use the proportions that are written on the screen, where a mole of a certain substance is equal to the mass of that substance in grams divided by the gram formula mass. Or you can divide the number of molecules by 6.02 times 10 to the 23rd molecules. That's Avogadro's number. And this division will equate to the number of moles of a certain substance. Or you could take the volume of a certain substance in liters and divide that by 22.4 liters if it is at STP in order to find the number of moles. Now, in the case where it is not at STP, you will have to use Pufner, or PV equals nRT, or ideal gas law. Now, please do the problem below. All right, so the first step was to find the balanced chemical equation. Since we have Mg reacting with HCl, we know the product is going to be MgCl2 and H2. I think everyone here has taken Regis chemistry, if I'm correct, so I hope you remember that part as to how I got the product side of that chemical equation. Right, so let's move on. And then from there, we want to figure out the limiting reactant. Right here, the limiting reactant. And so we're going to set up some proportions to find that. So we know 10 grams of magnesium is going to react with 18.5 grams of hydrochloric acid. So in order to find out which one is going to be the limiting reactant, we can set up a series of proportions to figure out if 10 grams of magnesium were to react completely, how many grams of hydrochloric acid would we need to make that magnesium react completely in this reaction? So let's set up some proportions. We know that the gram formula mass of magnesium is 24 grams, and this is 24 grams per mole of magnesium. Now, this is also outlined right here. Mole equals mass in grams divided by GFM. Now, from there, now that we have done a dimensional analysis to convert it from grams of magnesium to moles of magnesium, we are going to want to multiply this by the mole ratio between magnesium and hydrochloric acid. Now, if we have 1 mole of magnesium right here in this chemical equation, there are 2 moles of hydrochloric acid being consumed with it. So this is in a 1:2 ratio, or 2:1 ratio in this case. So from there, we can cancel out the moles of magnesium, right? And then from there, we're left with the moles of hydrochloric acid that would have been needed to make magnesium react completely. And then from there, we can multiply this by the gram formula mass of hydrochloric acid. That is 36.5 grams of hydrochloric acid per 1 mole of hydrochloric acid. that will yield 30.4 grams of hydrochloric acid that is needed to make 10 grams of magnesium react completely. This means that the limiting reactant in this case is hydrochloric acid. Since we know the limiting reactant is hydrochloric acid, we want to use our proportions involving 18.5 grams of hydrochloric acid to then figure out how many liters of hydrogen gas are produced at 25 degrees Celsius and 1.2 atm. So let's set up some proportions. We have 18.5 grams of hydrochloric acid, and we can convert this using dimensional analysis with the GFN to find the number of moles of hydrochloric acid. So we multiply this by 1 mole of hydrochloric acid per 36.5 grams of hydrochloric acid, and that will yield whatever number of moles of hydrochloric acid. From there, we know that for every 2 moles of hydrochloric acid consumed, right here, there is 1 mole of hydrogen gas being produced. This is a 1:2 ratio, and so from there, you can multiply this by 1 mole of hydrogen divided by 2 moles of hydrochloric acid, and this will convert our moles of hydrochloric acid needed to moles of hydrogen being produced from this reaction. Now we're going to solve it from here because, as I said before, the 22.4 liter to volume of whatever solution equals the number of moles of that substance. This only applies for conditions of standard temperature and pressure, which is not met at this case because this is 25 degrees Celsius and 1.2 atmospheres. So from there, we can use the ideal gas law, PV equals nRT. We isolate the volume since that's what this question is asking for, how many liters. And then from there, we can plug it in. N, number of moles, that's 0.253 moles of hydrogen gas. R, which is 0.08206, whatever units. And then from there, you multiply that by the temperature. 25 degrees Celsius plus 273, that is 298 Kelvin. And then we divide this all by the pressure, which in this case is 1.2 atm. And then from there, we find the total volume to be 5.16 liters of hydrogen gas produced at 25 degrees Celsius and 1.2 atmospheres in this reaction. Now, Natalie, Natalie, you said 5.16 liters. Good job. That was correct. Does anybody have any questions about this? All right, I'm going to take silence as a no. That's where I'm going to end it today.